Our next speaker is Abhishek Banerjee. He's going to talk about Quasimodular Hecke algebras.
Okay, so my work on Quasimodular Hecke algebras, it is grounded in the work of Kohn and Moscovici on modular Hecke algebras, where they constructed this non-commutative algebra which contains the Hecke operators and has coefficients in modular forms. So they had these two groundbreaking papers, so my work is in terms of quasi-modular Hecke algebras, and we'll see that when we use quasi-modular forms, we get essentially two kinds of operators. We again have Hopf algebra actions, but we have two kinds of operators. One is the bunch of operators coming from the fact that the operators. So a quasi-modular form has basically, as we will see, it has two parts. There's a modular part, and then there's a G2 part that's coming from the Eisenstein series. So we'll have two kinds of operators. One the old set of operators which are already acting on the modular Hecke algebra. Those are the operators coming from the modular coefficients part. And then we'll have new operators that we will see which are acting on the Eisenstein series. And so we'll have two different Hopf algebra actions. And we'll see that although the two Hopf algebras are, they're completely different, but the way we approach them in spirit, there's a lot of similarity, as we will point out as we go along. Okay, so we of course mention here, we mention quickly the modular Hecke algebras of Kohn and Moscovici. So they construct, this main construction they start with is having the modular tower, which is the direct limit of modular forms across all weights and all levels. So you construct that, and then the modular Hecke algebra consists of operators of finite support. So it's from gamma GL2 plus Q, so it's invariant on one side with respect to gamma, and on the other side, if you apply the gamma of level gamma, when you're talking of level gamma, it's f alpha gamma is f alpha bar with gamma. So this is the basic idea of the modular Hecke algebra of Kohn and Moscovici. Now we want to talk about a quasi-modular Hecke algebra. For that, first of all, we need to mention the structure theorem for quasi-modular forms, which is Kaneko and Zagier. So we recall quickly that the classical Eisenstein series, so that is Gk of Z. It's the Bernoulli number plus, as you can see, it's sigma of k. So it's the divisors raised to the k minus 1th power. So that is the classical Eisenstein series, and this is the. And so the key is that every quasi-modular form in Qm gamma can be written uniquely as a polynomial in G2. I have a feeling I'm missing one slide. Yeah, I thought so. I thought my thing was going a little faster than yeah. So there was another slide, and I pressed it too hard. Okay, so this should be the first slide. Yeah, I thought it was going a little faster than yeah. So this is the upper half plane. Yeah, so one should have a more. I think I made a better introduction. Yeah, I thought I had a better introduction. So we had this upper half plane, and of course there's the SL to Z action on it, and so we take, so that is the principal congruent subgroup gamma n, that is ABCD, where ABCD is congruent to 1 mod n, and then so this is the first definition. This is the explicit definition of a quasi-modular form. That is, it is a holomorphic function f from h to c. F is the quasi-modular of level n, weight k, and depth s, if it has that property. That is, you take the Cz plus d to the k. If in the case of a modular form, it would just be equal to f of z. But in the case of a quasi-modular form, you have that sum. You have a bunch of holomorphic functions fj, and of course, if you want depth s, you will assume that fs, the top one, is not equal to 0. It's like a polynomial, right? You assume that the top term is not 0. Otherwise, it makes no sense. And then this covariance property holds for ABCD in gamma. No. In the case of a modular form, S would be 0, and F0 would become equal to F. In the case of a modular form, yeah. So F0 is so this is the definition of a quasi-modular form, and as you can see, the quasi-modular forms, they would carry these natural product structures. That is, you just add up the weights and you add up the what is the other one? The depths. You add up the weights and you add up the depths, and similarly, you can just construct this sort of quasi-modular tower, that is, you add up quasi-modular forms of all weights, all depths, and all levels, and you take a direct limit. Okay. So this is the main object that we'll be talking about. So these are the quasi-modular forms. Okay. Okay. So now the reason we are doing this is in analogy. Now the next slide actually comes up. That is in analogy with the yes. Yes. So I have thought about it. I mean, so modular forms ordinarily would be the sections of a line bundle over gamma over H, but yeah, but tensor powers of the same line bundle. Those are the different weights, no? And maybe if you take the tensor algebra and consider its global sections, then you get all the. So I'm not particularly sure if you can create some, but maybe if you take something like if you take the basic line bundle that gives me the modular forms, and then you create some kind of. So if you have a module, right, and you can add an element to a module and sort of create something called mx, right? Just like you add something to an algebra, right, and you get ax, so you create something with an sort of mx, m plus mx square and all, and I believe it might give you the quasi-modular forms, because that will become more clear when we express them in terms of polynomials in G2, why I'm saying that. Okay. So I believe, but I don't have a proof of this, and but I believe that, you know, you take an m and you add an indeterminate to it, take that line bundle and sort of add and then go on each level, then you will get the quasi-modular forms, and that will become clear from why I'm saying that. So we have, so this is this quasi-modular tower, all modular forms of all levels. This is in analogy with the modular tower created by Kohn and Moscovici, where we have this, we take the modular forms of all weights and all levels, and we consider the direct limit that we call M. And then the modular Hecke algebra comes in, where you take functions on gamma GL2 cross GL2 plus Q, and you take the coefficients in M. Now, ordinarily, if you were forming a classical Hecke operator, you would just be taking coefficients in C, right? Then you would just get those double cosets. So that's what you would get. You would get, that's a classical Hecke operator. In order to get a modular Hecke operator, instead of C, you take coefficients sitting in M. And on the right side, you introduce another condition. That is, you say F alpha gamma is F alpha operated with gamma. Okay. So this is their definition. And now, so when we talk about quasi-modular forms, we have this structure theorem for the quasi-modular forms due to Kaneko and Zagier, where they say that if you take the Eisenstein series, this is you take the definition of the Eisenstein series, and so every quasi-modular form in QM gamma, it can be simply written as a polynomial in G2 with coefficients in M gamma. Okay. So this is the main structure theorem. That is, you take a quasi-modular form, so you can express it simply as a polynomial with modular coefficients, where the powers are polynomial with coefficients that are modular form, and then you have the powers of G2i. Okay. So this is why I think, you know, some such method might succeed, taking the line bundle, adding an indeterminate, and somehow going with it. So
you guys use G2.
Yes. So G2 is, so basically now you can see what our strategy is. We'll have two sets of operators, one acting on the AI parts, that will give us the old action on the modular Hecke algebra, and then we will deal with the G2. That will give us another set of operators. And basically, what we will see is that the previous Hopf algebra, the algebra that Kohn and Moscovici used, in that they were working with they had this operator which was working with this difference of, they took the modular discriminant delta, and then they took some matrix, delta gamma, and then they considered this difference, delta gamma minus delta. And we'll see that the role of that delta will be played by powers of G4. And how does G4 come into the picture? G4 comes into the picture. Remember that G2 is not a modular form, it's just a quasi-modular form, but G4 onwards, it's all modular forms. And the way G4 comes into the picture is that G4 comes in the expression for the derivative of G2. And starting from that, we'll see that whatever was so although the Hopf algebras are different, in some spirit, the approach is similar, because there they were taking the modular discriminant and considering delta alpha minus delta. And here we'll be working with G4 and actually all powers of G4. G4 alpha minus G4, and we'll be seeing that's how it goes. So, but for that first we have to introduce the definition. Yeah. So we quickly define a bar operator on that, and the bar operator is obviously very simple. You take a quasi-modular form, you just apply that. So you just take the modular coefficients and apply that bar operator. So
G2 is embedded.
yeah, G2 just is that. So this is very simple. So the definition is almost immediate. That is, you just take the same definition, and instead of f alpha gamma being f alpha 1 bar, you just put 2 bars. That's okay. So, and then what we can check. So what we will do is we will define 2 algebra structures. So this is the first algebra. So as you can see, this is basically a convolution algebra. So this is the first structure, and you can see that the coset representatives are taken over all of GL2 plus Q. This is one product structure. But we will also consider a second product structure. What is the difference between the product on top and the product below? It's the cosets that we are summing over. On top, we are working over all cosets in GL2 plus Q, but below we are working over all cosets in SL to Z. And we'll see that there is a lot of simplification when we work with SL to Z, because those difference operators, they disappear. Because for instance, if you are considering G4, and then you take G4 operated with some matrix alpha in SL to Z minus G4, that just becomes 0 when alpha is in SL to Z. And so there will be a big Hopf algebra, and there will be a small Hopf algebra sitting inside it. So those difference operators, they will go away. Yes. So we need a smaller Hopf algebra to act on this. So we'll always have a parallel one, which will be more like we'll always have a footnote attached. Each time we prove something for the bigger one, we'll just mention that a smaller Hopf algebra would work if we consider this product. And one notation that we'll make is how to distinguish between these structures. Whenever we are using this smaller product structure, we'll call it QR gamma. Okay. The same algebra. So Q gamma is an algebra with that product, but whenever we use the second smaller product structure, we just call it QR gamma, just to distinguish which one we are using. Okay. So quick observation is that obviously the ordinary modular forms would embed inside the quasi-modular forms. And so it is quite clear that there is a natural embedding of the modular Hecke algebra, A gamma, inside Q gamma. And of course, one should mention that just like the modular Hecke algebra acts on M gamma, the quasi-modular Hecke algebra also has a very similar action on the QM gamma. So basically, it's a Hecke operator. The first thing it's supposed to do is supposed to act on modular forms. So in this case, there's a quasi-modular Hecke operator, and it acts on quasi-modular forms. So this makes QM gamma a left module over Q gamma. So now we start considering the operators. Okay. So as we said, we'll consider 2 kinds of operators. So first, we'll start by considering the new operators, which are acting on the G2 part of the quasi-modular form. Yes. So we are starting by showing the operators. So we first consider the operators on the G2 part. Now we know G2 is a quasi-modular form, so its derivative is a quasi-modular form directly. Unlike modular forms, whose derivatives are not modular forms, in quasi-modular forms that is there. So what we notice is that G2 prime, in fact, is equal to, so that's the formula, 5 pi over 3 G4 minus 4 pi I G2 squared. Minus 4 pi I G2 squared, and as you can see, we have written it as a polynomial with coefficients in powers of G2. So G2 squared is the top term, then the 1th term just isn't there, it's 0, and then at the 0th level, because recall that G4 is modular. So as you can see, that's G2, so it's 5 pi over 3 G4 times G2 raised to the 0th power. So that's the 0th, so that's like the constant term of that part, minus 4 pi I G2 squared. So as you can see, so whenever we take the derivative, the G4 naturally comes into the picture. So, okay. So now we take some quasi-modular form F, and then the first operator we call it D. So what it does is, so it's got the modular form AI G2I. So it's AI G2I. It just differentiates the powers of G2. So what do I have? Instead of G2I, in place of G2I, I simply get I G2 to the I minus 1 times G2 prime. Right. So that's simple enough. And of course, then you can rewrite it by using the fact that G2 prime can be written as that formula. So you have to rearrange the powers a bit, and so that is the first operator. It simply takes G2 to the I G2 I minus 1 G2 prime, and then so again, this is in spirit similar to what they did. That we consider the second bunch of operators. those are weight operators. In the theory of Kohn and Moscovici, they have only one weight operator. But this case, we consider a bunch of weight operators because we have to compute the commutators. So in order to have the commutators, what works out is that, because see, when Kohn and Moscovici had their theory, they had the differential operator x and the weight operator y. And it nicely worked out that yx became equal to x. But we don't have something like that. Here we have to sort of create a family so that we can stay within the family, because it's not working out that way. So what we do is, so we have a weight operator again, that is in place of g2 to the I. For g2 to the I, the weight I assign to it is I, but then I also have to create a whole family. That is, the kth weight operator will also change that power by k minus 2. So this is what we need. So, so those are the weight operators. They take I and then g2 I to the k plus 2, I plus k minus 2. It's very easy to check that there are derivations on QM. And now, in order to consider these, we'll have to define these objects. And we'll see these are the parallels of those objects which are constructed with the modular discriminant. That is, you take the powers of G4 and you define these new objects. New alpha m, you define it as, so that's just a scaling factor, 5 over 24. That is, and it gives you G4 to the alpha minus G4 to the m. So G4 is a modular form. The powers of G4 are also modular forms. So in the case of alpha, for any alpha in GL2 plus Q, we just consider those differences. Okay? And the first thing to notice is that nu alpha beta, this property is satisfied. This is immediate. This is, oh yeah, so this is the cocycle, is immediate. And then of course, because the G4 is a modular form and its powers are also modular forms, if you took alpha in SL to Z, then of course it would become 0. I mean, that is the whole point of making it 0 when it is in SL to Z. So these are our basic operators, and then we have to start talking about commutators. So now, so basically we have to justify why we constructed these objects. We constructed these objects because the first question is, when I define this operator D, the question is, how does D interact with that bar operator? So if I take D of F and then apply alpha, is it the same thing as D of F operated on alpha? So how does that work out? So when we do that, we see that that difference is computed in terms of nu alpha 1. That is, D of F alpha minus D of F alpha minus D F alpha is nu alpha times this. And as you can see, this is actually very similar to the formula with the X, where in the case of, so when we'll come to the part with the H1 action, we'll point it out. This formula is actually very similar to the formula in terms of the Ramanujan differential operator that they obtained in. And in that case, instead of G4, they just had delta, which is the modular discriminant. Okay. And here nu alpha 1 is equal to minus 1 over 8 pi I G0 minus this, and then this scaled up. This is just scaling. Basically, that 5 over 24 factor was done so that this would just become 1. Okay, so that's just scaling. And this is very easy to check that the weight operator has no impact on the alpha with the bar operator. So now we have to define these operators. So we already have D and WK. We
somehow, your WK is composed from W1 and something which is
it just steps up the power by, so it's basically a shift operator. Because if you think of the polynomial as just things put in place, it's just basically it's just W1 with some shifts. So we need those shifts in order to make the commutators work.
you don't want to separate the shifts?
No. Actually, in fact, we'll be putting in something else as well and making it even more composite. So, and in order to take into account these objects, nu alpha 1, I have to create this family of operators phi m, where phi m of f alpha is nu alpha m f alpha. So to create this, so these are my 3 operators, but we will refine it slightly more. In fact, this is still not enough to compute the commutators. We will have to actually need one more operator. That is Qm to Qm, it just multiplies with G4. So this operator is very simple because G4 is already a modular form. It does not disturb the powers in the polynomial at all, but we need this. We need f going to G4f, and we call this operator E. And so E from Q gamma to Q gamma, it simply multiplies G4 times f alpha and so forth. And now we compute the commutators. Now on top, obviously the top, these things are just 0, but this is the main one. That is ELWK this thing comes out in terms of this. So you'll have to sit down and work this out. So this is the commutator. Now, as you can see, in order to even to simplify this thing, what we really need to do is put the E and the W together. So what we really want is those operators Tk. That is, I take Tkl equals E to the LWk. I just put them together. So this is just making it shorter, reducing the number of things up there. So now we just have this Lie algebra, and we have, so on top these are 0, of course, and this is the main relation. And we consider this Lie algebra, and this Lie algebra has an action on Q gamma. And how does the Tk act? So we have to check how it operates with the F alpha, and so we have this thing coming out. Okay. So this is the relation with the F alpha, and this is the most important part. That if I, so now the question is, how does this operator Tkl interact with the product? Because so now so till now we were at the Lie action level because we were just computing commutators, but now I want to go to the Hopf algebra level, so I have to start working with products. So I have to now start working with products, and so this is what we sit down and compute. Tkl F1 F2 is simply yes, computing yes, and so this is the basic derivation kind of thing, F1 F2 F1 F2, but then this is the extra term that sits here. No, it's not symmetrical. Yeah. So as you can see, although the explicit things are different, in spirit it is similar to what was done. So in the case of modular Hecke algebras, and again, and quickly we mentioned that instead of Q gamma, if we use the reduced product QR gamma, then obviously we were just working with matrices in SL to Z. Then we wouldn't need those extra covariance terms, and this would simply be a derivation. So this star R that you are seeing, this is the sort of I don't want to call it restricted product because it has a specific meaning, but it's just star R. So it's just it's just a smaller product. Yeah. So if I take the smaller QR, then it's just a derivation. And if I have the whole Q gamma, then I have an extra term. Okay, so now we have to reconcile everything inside a Hopf algebra. So as Hopf algebra, yeah. So basically this, so I take H equals, so H has to be simply as an algebra, it's just the universal enveloping of the Lie algebra with those relations. And then I put these on, and to define these, I put this. This is antipode. And the way to extend the coproduct is this formula. Now, one of the fun features of this formula is that you notice that the denominator here is k minus 3, which means it doesn't work until k is greater than or equal to 4. Or more specifically, only when k is equal to 3. It's just that 3 is so small that until 3, I just define them literally by hand. I just wrote down. And from 4 onwards, you can just define this. And similarly for the antipode. Yeah. So 3 is small enough, and beyond that it is. Okay. So this is the Hopf algebra. Okay, and of course so we mentioned here that it has a little brother. So you throw out those operators phi m, and then you have a smaller Lie algebra. This L, it's just the same algebra, just without those operators phi m. It has the same relation. Now the key so now the operator D, how does that interact with the product? We did not mention that. So when we apply that, so df1 f2 is df1 f2 f1 df2, and then this is that other term. So this thing, and now looking at the expression for the coproduct, and really we wrote down the coproduct specifically to coincide with this. So, and of course, once again, if we use this smaller algebra structure, that is star R, then again D simply becomes a derivation. So there's nothing to think about. It just becomes the universal enveloping algebra of a Lie algebra in the case of the smaller one. That is really easy. And so for the big Hopf algebra, then we have this Hopf action structure. That is H F1 F2 is H1 F1, H2 F2, where H is the coproduct and all. Yeah. So, and of course, if I use the smaller Hopf algebra that is coming simply from the smaller Lie algebra, of course, it has a Hopf action on the QR gamma, on the reduced smaller algebra. Okay. So this is the actions so these are the actions coming from the G2 parts. And now we go back to the case of Conrad-Moscovici, where we will consider the operators coming from the modular part. So for this, we just have to recall what they did. So this is the Hopf algebra H1 defined by them, and now we will consider operators on Q gamma coming from the modular coefficients AIF of the quasi-modular form. And H1 is, of course, yeah, so H1 is part of a larger family, H1 constructed by them. And so as an algebra, H1 is the universal enveloping algebra of this Lie algebra. And then you have delta X. You can see again the co-products are tailored to fit in to the formula. And this is the antipode. And we know that H1 has a Hopf action on A gamma. And it is to be expected that it is going to have an action on Q gamma, which we will now describe. So, okay. So again, here you have the weight operator Y going from mk gamma to mk gamma. So as you can see, this is a weight operator, the first operator Y. But what is it measuring? It's measuring the weight of the modular form. But our weight operator, when we had, it was measuring the weight of the G2 because it was taking G2 to the I to I times G2. So this operator measures the weight of the modular part, and that operator which we are defining WK, it measures the weight of the G2 part. So that is one operator. And then there is the differential operator. Of course, when you are working with modular forms, you need a slightly modified version of the differential operator. And what I want to show is, okay, so they were using this. So they were using this object that is delta, which is, so basically whatever works happens with delta in this theory was happening with G4 in that other theory. Because as you can see, you look at this formula, xf alpha is, so here they consider the derivation x and then consider its interaction with the bar operator. You have this formula, and this is supposed to be the parallel of, where is it? This is supposed to be the parallel of this. Okay. So you have x and xf alpha interacting, and here you see this mu alpha term. And where does this mu come from? Mu comes from taking delta gamma minus delta. In that case, we were taking G4 to the m minus this. So we have this object, and of course the weight operator quickly commutes. So, okay. And then you had these operators, x, y, delta. And so with the basic difference, this operator, now look at this operator, delta n f alpha is xn minus 1 mu alpha f alpha. This is supposed to be the parallel of this operator, this one. Yeah. And yeah, so we have this, and so these are the three operators. The only difference is that here we have only one weight operator, and there we needed a bunch of weight operators because the whole commuting, it, whenever you try to compute the commutator, it keeps going up and down in the family. So we needed some shift. So basically, we needed some shift operators too. So, okay. And then once again, this is the larger Lie algebra, and then we have a smaller Lie algebra, which just consists of y and x. It doesn't have the delta n's in it. So it's yx satisfying yx equals x. This is a very small algebra. And then H1 is its universal enveloping algebra. So, and L1, it has a, and so this L1 obviously, because the operators are constructed that way, this L1 obviously has a Lie action on the module Q gamma, on the quasi-modular thing Q gamma, and so obviously it does the smaller Lie algebra. And if you explicitly write them down, it is this one. So the operator x on this algebra, it satisfies xf1f2, xf1f2. Plus this is the extra term that comes in, and again this is supposed to be the parallel of this formula, this one. In this case, the differential operator satisfies this formula, and in this case we get this formula. And once again, when we have star r, when we consider the smaller product, then everything becomes a derivation like usual. So we have xf1 f2 is xf1 f2 and f1 xf2. And so quickly you can say that now that everything that the co-products have been constructed that way, once again you have this other Hopf algebra which also has a Hopf action. That is, you have h f1 f2 is h1 f1, h2 f2, then so this is the product. And similarly, if you took the smaller Hopf algebra, it would have a Hopf action on this smaller structure. I mean, QR gamma is not smaller, it, as I said, it's just smaller as an algebra in some sense.
But the product stuff, is it commutative or not?
No, no, no. No, there's no question of commutative.
That's why the co-product is not.
Yeah. Yeah. Okay. So now this is a, So now what we want to do is, so till now we were working with algebras. We were working with modular Hecke algebras, quasi-modular Hecke algebras. Now I want to define modules by taking some kind of perturbation of this, some kind of twist, which is what I call a twister. Maybe I could have called it a perturbation. Yeah, sure. Yeah. So because basic idea is the quasi-modular form has two parts. It has modular coefficients and it has powers of G2. On the powers of G2, you have one half algebra acting, and on the modular coefficients, you will simply have the old H1 action extended. So just carry over from that part. So you'll have both. And I don't know, maybe if you prefer a single half algebra acting, maybe you can take the tensor product of the two half algebras. I don't know. Yeah. So yeah, that is what I mean. I tried to compute that, and that really goes into there's just too many commutations. It just doesn't work. Yeah. So okay. Yes, so I did try to compute the commutators coming from the modular part with the operators coming from the G2 part. It's just all over the place. There is no way to, the two actions don't mix. So, okay, so now we want to construct this sort of perturbation of these quasi-modular Hecke operators, and we want to sort of move them, twist them by a term of in SL to Z. So what we define is this object. So we take a sigma in SL to Z. For sigma, we want to define this collection Q sigma gamma of quasi-modular Hecke operators of level gamma twisted by a certain sigma. Of course, when sigma is identically equal to SL2 is equal to 1, then Q sigma gamma simply becomes equal to Q gamma. And so how is it defined? Sigma twisted quasi-modular Hecke operator F of level gamma, it is a function of finite support. So once again you have this, but you just see the difference in this one. That is, on this side there is a slight difference. F alpha gamma, this is F alpha sigma gamma sigma inverse. So there is a twisting inside that action.
Not like conjugated by without the multiple?
Hmm?
No, because sigma doesn't commute with alpha.
I know, but sure, no, but what I mean is that in the algebraic sense, it's not like you will get an algebra which is not isomorphic.
This is actually not even an algebra. It is a module over Q gamma, but it carries a pairing. There's no, I mean, this is specifically a module. This is not at all a. So. Yeah, that's exactly what I'm saying. So Q sigma gamma, it is not an algebra, but it carries a pairing, and this pairing, I mean, this is not associative in any sense. That's why it's just a pairing. And I mean, I tried a lot to prove that it is an algebra, but it's not. And we have, yeah. So we just have this here, and you see that there are some changes over in this space. And this is a pairing, and with this Q sigma gamma, it is a module over Q gamma, but on the right side. So there's a difference. What? I don't understand the question.
You have an algebra, the algebra is modular on itself. Okay?
Yes.
Then I can change this modular structure artificially by multiplying by the invertible element in the algebra.
It is possible. I mean, I have to see.
I mean, you would have to prove that
Yeah.
it's a module.
Yeah. It is possible. I mean, I'm not sure. So we have this pairing, and then we have this. Of course, once and again take x and y satisfying this, and then we take the h1, which is the universal. This is already mentioned, and so you just extend these operators x and y acting on this, and you can show. So instead of the pairing, I mean, last time we had a product, and we showed that there was a Hopf action on the product. That is like this. Hf1 f2 is h1 f1 times h2 f2, and in this case, instead of a product, you just have a pairing. So you just have a comma over there instead of a star, and so you have f1 alpha over this, and it's just where the coproduct is given by this. So we have this action. Yeah. So Q sigma gamma, it carries a right Q gamma module structure, which is defined by this f1 star f2 on this side, and you have f1 f2, and we can describe the action similarly of H1 on this, or by x, y, and delta n. So you have this structure, and you can see there's a twisting here as well. You see that this says mu alpha sigma inverse over here. Last time it was mu alpha. And so here there's a mu alpha sigma inverse f alpha, and then it has just the right action, and once again, not only that, this time it is a module action, right? So this side carries a product when you have the F2. So notice that the F1 is from Q sigma and the F2 is from Q gamma, and if you take the Hopf algebra H1, it has a Hopf action on the right Q gamma, this object of Q gamma. Okay. And now the main reason I wanted to construct this is I wanted to go up and down inside this object. So you have these operators x tau, which take you from, we change the twist, that is they go from Q sigma gamma to Q tau sigma gamma. And for each tau and sigma in SL to Z, you consider Q sigma going from Q sigma tau. Now here the commuting matrices come in. So basically what I want to do is, once I construct these operators x tau that go up and down, I want to compute the commutators of these operators x tau. Now of course, if I am going from Q sigma to Q tau 1 sigma, and then going all the way to Q tau 2 tau 1 sigma, that thing cannot possibly commute unless tau 1 is equal to tau 2, if I just take the operators in the opposite direction. So I have to have commuting operators. So I take tau 1, tau 2 in SL to Z such that tau 1, tau 2 is equal to tau 2, tau 1. And in that case, x tau 1 and x tau 2, they just commute, one can show. And once I have commuting, I mean, the most obvious commuting family in the world is this family. That is, rho n is equal to 1 n 0 this. And we set sigma n equals rho n sigma for any sigma in SL to Z. And we want to define an extended version of this pairing on this graded module. That is, Q sigma gamma is, you take the sigma and you just apply the various rho n's, and you just put them in a sort of in a row, and you want to consider this graded module that extends the pairing on Q sigma gamma. So you take tau 1, tau 2 in SL to Z such that tau 1, tau 2 is equal to tau 2, tau 1. Then you have a general pairing, that is Q tau 1 sigma, Q tau 2 sigma going to tau 1, tau 2 sigma. And here tau 2, tau 1 is equal to tau 1, tau 2. And it is defined as follows. You can sit down and you can actually check this. So this works. And if you put tau 1 equals tau 2 equals 1, this just reduces to the pairing back on this. And in particular, since you have tau 1 and tau 2, in the case of m and n, that is, you just consider two elements from this family, sigma m and sigma n, then you have Q sigma m, Q sigma n going to Q sigma m plus n. And this induces a pairing on this larger object for each sigma in SL to Z. And finally, we have this Hopf algebra action on Hz. That is, in particular, when you take the Q sigma m and you take it n steps, you just call it xn. And you have the second operator Z. Now, this is like the previous weight operator, that it just takes f to f alpha, but it also, actually, this is the old part, that is y f alpha. And to that, you also add the weight coming from the place that you are in. That is, if you are in sigma m, you add m. So m f alpha, and then the y f alpha is there. And so this operator is obviously homogeneous of degree 0 inside. And then you take this Lie algebra. So last time, remember, we had the old Lie algebra that was yx equals x. Where is it? We had yx equals x. Now this time we have a slightly bigger Lie algebra. That is, we have the operator xn and we have z. And what do they satisfy? Z xn equals n plus 1 xn. So in particular, if you took n is equal to 0, you would have zx0 equals x0. That is, you would have the old Lie algebra sitting right inside. So here you have a bigger Lie algebra. So in place of L1, because that had only one differential operator, I call it Lz. And so you have zxn equals n plus 1 xn, and the other xn's commute, in particular zx0. So Lz contains this Lie algebra. And so this Lie algebra Lz has a Lie action on Q sigma gamma, and you let Hz be the universal enveloping algebra of Lz. And one last thing that you want to compute is how this interacts with the pairings. So here again, you can sit down and calculate this out. If tau 1, so now you need three operators, right? You have Q tau 1 sigma, Q tau 2 sigma, and on that you want to apply x tau 3. So you need three matrices. So I take three matrices, tau 1, tau 2, tau 3, that are all commuting with each other. Tau I, tau j is tau j, tau I. Then you can actually sit down and calculate this, that x tau 3 f1 f2 is x tau 3 this, x tau 3 that. And so in particular for xn, if you put tau equals rho n, then you have this. And you have finally, if you take the hz, which is the universal enveloping algebra of Lz, then it has a Hopf action of this. So thank you. Yeah. Yeah.
I mean, the reason why we were doing this with Henri was the following: that
Yeah.
first of all, the Hopf algebra H1 already existed.
Mm.
The Hopf algebra
Yes.
complex geometry.
Yes. Yes. Yes.
Okay. And then the second thing, which was very important, is that what we found is that okay, so it's acting on this modular Hecke algebra.
Mm-hmm.
But what was very important is that the characteristic map from cyclic homology of the Hopf algebra to the homology of this modular Hecke algebra was very interesting.
So those cocycles.
So here there are. So the first obvious question is the following. First of all, this larger Hopf algebra that you get.
Are you talking? One second. Are you talking about this one?
First one.
This.
The first one.
This.
Does it have geometric meaning?
I mean, I'm not. I mean, this Hopf algebra really has been constructed in analogy with that H1. Other than that, I don't. No, I don't have a direct motivation for. In fact. Yeah. Yes. Yes. Yeah.
So is it the same? Is it the
I mean, I'm really still struggling even with this H1, because one thing I should mention is that this is not the only commutator relation. You see, I'm even hiding a secret commutator relation that I have not put up here, because as you can see, everything else is up here. You have d phi m, t phi m, and phi m phi m. But if you notice, there is one thing that is missing. That is, how does TKL operate with TK prime L prime? The commutator relation for that is TKL, TK prime L prime. I'll just write it down. It is yes, yes. So it just takes a second to write down. So the relation there is if you take TKL, TK prime L prime, it's not that it's impossible to find. This is equal to, if it's either k minus k prime or k prime minus k, but k plus k prime and k plus k prime minus 2. This is the third commutator relation, but I'm having some difficulty somehow in absorbing it into terms of those co-products. That is, for the moment, I'm even suppressing that commutator relation. But but it does fit very nicely inside the Lie algebra structure without any problems. But I'm having some, so I'm even expecting to change this Hopf algebra a little. So not even.
Yeah, but so I mean, the program should be the following instead of.
Yes. To find some geometric meaning of.
Okay, then what you have to find is what is its structure? Is it a bi-cross product?
Mm-hmm.
Does it have geometric meaning? And then compute its cyclic homology.
Yeah.
And then, okay, I mean, the next step also is to put the two things together because they act on the same algebra.
Yes.
If they act on the same algebra, they have to generate, it's a very general fact that if you have a bunch of operators which are acting on an algebra,
Yes.
and you can express the action of an operator on a product as a linear combination of products of terms.
Could you repeat one more time?
What I'm saying is that, because this is stable by product,
Mm.
what I'm saying is that you have an algebra, okay?
Mm-hmm.
And you have linear operators acting on that algebra.
Yes.
And they have the property that if I apply this linear operator to a product of two elements,
Mm-hmm.
I can rewrite the result as a sum.
Yes.
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 Okay?
Yes. Yes. Yes.
This is the case.
Yes.
It's a case separately.
Absolutely. Yeah.
But it's a case separately, but it's also the case when you take all of them together.
Mm-hmm.
So because
Yes.
of that,
Yes.
you know that you have a Hopf algebra.
Yes.
When you combine them. Now what you have to do is to compute the presentation of the
Yes.
Hopf algebra. And then you have to compute
Yes.
the cyclic homology.
Yes. I mean, mixing
There are
up
lots of
those.
things to do
Yes.
directly,
Yeah.
not
So.
embarking into
Yeah, so to put those two actions together, I mean, basically what is happening is, the powers are getting scrambled with the, yeah. So one has to compute these commutators.
There would be one of these things. When you look at the Hopf algebra H1, because you
Yes, yes. That thing has not been touched. Yeah. That has not been touched yet. No. Because the structure of this Hopf algebra I have not really fully understood at all. I mean, yeah. I really just have the relation, sir, at the moment. I need to understand this Hopf algebra much better.